Today we're going to talk about 4.6. Here is your bell work if you want to go ahead and pause the video and work through this bell work here. All right, now that you have paused it, we will work through it together. So with this one, you have two different bases, and your exponents are both binomials. And if that's the case, it's not going to matter which one you cancel. And you actually don't have to cancel either one. We could take the ln of both sides here. So with this one, I'm just going to cancel this side over here. And in order to do that, I'm going to take the log, the common log of both sides. So we have log 10, 1 minus x equals log 6, x minus 1. Now with this one, your log and your base 10 cancel and you get 1 minus x. On the right side here, we're going to bring the exponent out front. So x minus 1 log 6. And with this log 6 here, I need to distribute that inside to both of those terms. So we have 1 minus x equals x log 6 minus 1 times log 6, which is log 6. Now I have multiple x's, so in order to do this, we need to get our x's on one side, and we can put the numbers on the other side. So I'm going to add x to this side, and I'm going to add log 6 to this side. So these cancel here, but your log 6's cancel there. So we have 1 plus log 6 equals x log 6 plus x. Got x's here, so I'm going to factor it out. Log 6 plus 1 equals 1 plus log 6. And then we will divide by log 6 plus 1. And then 1 plus log 6 divided by log 6 plus 1. Those are the exact same thing, so you get 1. So x equals 1. If we plug that back in, you get 1 minus 1 is 0. So 10 to the 0 is 1. And 1 minus 1 is 0. 6 to the 0 is 1. So you get 1 equals 1. Okay. All right, so 4.6, 4.7, I put them in the same presentation, but we're only going to cover 4.6 in this video. And that's modeling with exponential and logarithmic. So 4.6 is the exponential, 4.7 is the logarithmic. So our goal here is to use both functions to solve real-world problems. Now that's just a fancy way of saying word problems. Okay, so we need to remember how to solve equations of exponential and logarithmic. And in doing that, kind of one of the main things I say in every presentation is how to change from logarithmic to exponential. So here, if I have logarithmic, to change to exponential, we kind of go in that circle. So I use the same base to the y or to the equals. So x to the y, because a logarithm is an exponent, equals b. So knowing how to rewrite exponential to logarithmic and logarithmic to exponential is important. So I'm going to front load this presentation here with all the formulas that you'll need to know for these examples. So the first one here is doubling time. Doubling time looks like P of t, which is population after a given time, equals P naught 2 to the t over d. Okay, and we said this was your population or your number after time. P naught or P sub 0 is your starting number or your starting population. 2 is there for your doubling time. T is time. And D is the amount of time it takes to double. So we call that doubling time. Now note that these two need to be the same label or the same units. whatever they are, days, months, weeks, years, hours, seconds, whatever it is, they need to be the same. The next one we have is half-life. Half-life is P of T equals P naught 1/2 T over H. Now this equation is pretty much identical, except with doubling time I have a 2, with half-life I have a half. T is still time, and H is your half-life time. Again, they are in the same units. Okay, and the half-life time is just the amount of time it takes to split something in half. Okay? So those are very similar. We also have another one that's very similar, or two more actually, but they're close to each other. And that is your relative growth or decay. Okay, and relative growth would be P of T equals P naught E to the RT. And decay would be P of T equals P naught E to the minus RT. And with R, they sometimes put a K in there, but notice the only difference is the negative. So T is still time, R is your rate or a constant if they give that to you. E is a natural number. P naught is, again, your starting population or your starting number, and P of T is your population after a given time. So these four are pretty identical to each other, especially these last two. These last two we normally see in this form. Okay, for finance problems, compounded continuously are these growths or decay. Okay, and then the last one we have is Newton's cooling law. And that is T of T equals T sub S plus D naught E to the minus KT. So we have this portion is kind of like this exponential decay right here, or relative decay right here, pretty close. And then we have our surrounding temperature. So T of T is your temperature after time. TS is your surrounding temperature. That's just you. That's the temperature of the air around. D naught equals your starting temperature minus your surrounding temperature. So T naught is your initial, your start temperature. K is some constant. It depends on the material that we're talking about, and T is time. Okay, and then I guess I'll put T naught is starting temperature. Okay, so these are 5 equations that we're going to use going through these word problems. Okay, so problem number 1 here says under ideal conditions, a certain bacteria population doubles. Okay, so doubles every 3 hours. Initially, there are 1,000 bacteria in the colony. Find a model for the bacteria population after T hours. How many bacteria are in the colony after 15 hours? After how many hours will it reach 100,000? Okay, so it tells me that it's doubling time because it uses the word double. So that means I'm going to use this initial, not E, 0, 2 to the T over D. Okay, I'm going to use this to kind of set something up. So find a model for the bacteria after T hours. Okay, it doubles every 3 hours, so that is D there. So P of T equals, my initial population is 1,000. 2, I don't know T, over D, which was 3 hours. Okay, so we're just plugging in numbers. Do not take 1,000 times 2. You still need to follow order of operations when you do this. So how many bacteria are in the colony after 15 hours? So I want to find P of 15. So that's 1,000, 2 to the 15 over 3. And then we can just put that into the calculator. And you get 32,000 bacteria. Okay, and the last one, after how many hours will the bacteria count reach 100,000? So we're solving for time, and we're setting this thing equal to 100,000. So 1,000 to the T over 3. So we're solving this for T. So I'm first going to divide by 1,000. So you get 100 equals 2 to the T over 3. Now here's where it gets tricky, because a lot of kids want to divide by 2, but you're not actually multiplying by 2. You have exponential here, and in order to get this out of exponential, we have to write it as a logarithm. So that's log of base 2 of 100 equals T over 3. And now we'll multiply both sides by 3. And you get T equals 3 log base 2 of 100, which is about 3. Don't forget, alpha window is how you can get to other logarithms. This is about 19.9 hours. Kind of got to go back and look at your label. What was T in? And T was in hours. Okay, so example 2. A certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100 and doubling every 3 months. Okay, so again, it's telling us it's doubling. So that tells me that I want the doubling formula. That would be T over D. But if you notice, it doesn't actually give me like the initial population. It says, what is the initial population? Estimate the population after 1 year, and then sketch a graph. Okay, we're not going to sketch a graph, but I definitely want to look at A and B. So I need to find the initial population. Okay, so I know that we've been on the island for 8 months, and we have 4,100. But I know my doubling time is 3 months. So I know everything except P naught. So if I solve this, I got 4,100 P naught 2, and I know it's been 8 months, so 8 over 3. Okay. Well, 2 to the 8/3, that's a number times P naught. So I just need to divide by 2 to the 8/3. Okay, so P naught equals 4,100 divided by 2 to the 8/3, which is about I get 645.71, and these are rabbits, so we're going to round down. Okay, so on the test, there will be kind of a range of values you can have, and I'm going to be looking through your work to make sure that you have the correct work with it. Okay, so estimate the population after 1 year. Now remember, these are in months, so I cannot use a year. So I actually want P of 12 because there's 12 months in a year. Okay, so my initial population is 645 to the 12/3. Okay, and just put that into the calculator. 2 to the 12/3, which is 4. We get 10,000 320 rabbits. Okay, and if you were going to sketch a graph, we would use this and put in our initial and our doubling time. We'd look at P of t equals 645 to the t over 3. That's the equation we would look at for graphing. The initial bacterium count in a culture is 500. Okay, so that's P naught. A biologist later makes a sample count of the bacteria in the culture and finds the relative, okay, that's a key word, rate of growth is 40% per hour. So we're going to use our relative growth, which is P naught E to the RT. Find a function that models the number of bacteria after T hours. Okay, and again, we're in hours. This is per hour. This is hours. This is hours. Everything's going to be in hours. So we have P of T equals 500. That's what we started with. E to the R, which is 0.4 times T. Okay, so there's our equation. What is the estimated count after 10 hours? So I want to know what is P of 10. And again, these match. My rate was in hours. My time here is going to be in hours. So it's 500 E to the 0.4 times 10, which calculator, type that in, 0.4 times 10. You get about 27299. And you can put decimals. You can put 0.08 if you want. Bacteria. Okay. All right. After how many hours will the bacteria count reach 80,000? So here we're setting it equal to 80,000, and we're solving for time. So 500 e to the 0.4 times t. So divide by 500. 80,000 divided by 500 is 160. E to the 0.4 t. To get it out of exponential, we write it into logarithmic. So that's ln of 160 equals 0.4 t, and divide both sides by 0.4. So you have t equals ln of 160 over 0.4, which is about ln of 160 divided by 0.4. You get about 12.69 hours. All right. Next example here. In 2000, the population of the world was 6.1 billion, and the relative rate of growth, okay, so that tells us right here what model we're using. So we have P of T equals P naught E to the RT, was 1.4 per year. It is claimed that a rate of 1% per year would make a significant difference in the total population in just a few decades. Test this claim by estimating the population of the world in year 2050 using relative rate of growth. Okay, so they give us 1.4 and 1, and we need to look at the relative growth in year 2050. So we have P of 50 because we're looking 2000 to 2050. So we want P of 50 in the equation. 6.1 is my start. E, and for this one, I'm using 0.014 times 50. That's my time. So this is 6.1 E to the 0.014 times 50. So this is about 12.28 billion. And then this one, P of 50 still, it's identical, but the rate is not 0.014, it's just 0.01 times 50, which is about, I get 10.06 billion. Okay, so yeah, that's a significant, that's, 2.22 billion people different over 50 years. Okay, so that's quite a bit of difference. Now, we're not actually going to graph it, but we can kind of see, I'll kind of show you here, that if you were to graph it, this red one here might start off something like this, might go like that. And then the blue one starts in the same spot, but slowly over time, they start separating. Okay, they start separating there. So in a few years, they're really close, but after 100 years or even after 50 years, they're 2.2 billion away from each other. A culture starts with 1,000 bacteria, and the number doubles every 40 minutes. Find a function that models the, okay, so here we're finding doubling time, so double time. And here we're finding the relative growth. Okay, I don't need a graph of these two. Okay, we'll just look at how they differ. Okay, so here I want in hours for both of them, but they give it to me in minutes. But we know that 40 minutes is 2/3 of an hour. Okay, so instead of using 40 minutes, I'm going to use 2/3. So here we have population T equals P naught, so 10,000 to the T over 2/3. Now, dividing by 2/3 is the same as multiplying by 3 over 2, which is 1.5. So if you want to write this 10,000 to the 1.5 T, you could do that as well. Okay, both of those are accurate equations. Now, when we go to relative growth, I actually don't have my rate, but I can find the rate. I need this rate right here. I know that it doubles every 40 minutes. Okay, so in 40 minutes, it's going to have 20,000. It still starts with 10,000. E to the R times T, which was 2/3. And we're going to solve this for R. So if I divide by 10,000, that's 2 equals E to the R times 2/3. Or you could, yeah. So now we need to switch out of the exponential and put it into logarithmic, and it's ln. So ln2 equals 2/3 R. And then we're going to divide by 2/3 or multiply by 1.5. So R equals ln2 divided by 2/3. So I have 1.0 4 is what it would round to. So then my equation here would be P of T equals 10,000 E to the 1.04 T. That way, whatever time that they give me, I can figure it out. Now, these will slightly differ on the graph, and that's why it kind of wanted us to graph it. They slightly differ. Okay, kind of like this over here differed on a big scale. These two would differ just a little bit. Okay, because here we're using 2, and remember E is 2.718. So we have just a little bit different values there. Okay, so here we have radioactive decay. So half-life of 140 days. Suppose a sample of the substance starts with a mass of 300. Now, the book used a little bit different formulas, so we're not going to use their half-life formula. It's identical to ours, just written a little bit differently. Um, but we do have the relative decay model right here. Okay, so for half-life, we have P of T equals our starting amount. So 300, 1/2 T over, and I want it in days, and my half-life time is 140. So there's my half-life formula. For the relative rate, we are going to, we still have to find R like before. So half-life, so I'm dividing it in half. So after 140 days, if I start with 300, then I have 150, 300 e to the negative r times 140. Okay, because it took 140 days to go half. So we're going to divide by 300. So 1/2 e to the negative r times 140. Get it out of e, so we're going to go ln of a half equals negative 140 r, and then divide by negative 140. So r equals ln of a half divided by negative 140. So we get 0.005. You could take that out to more decimals if you wanted. So for B, my equation would be P of T equals 300 e to the minus 0.005 T. Find the mass remaining after 1 year. It doesn't matter which one you want to use. I'm going to use this one up here, the half-life one, and it's 1 year. Okay, everything was in days, so I want to find P of 365. So that'd be 300, 1/2, 365 over 140. So 300 times a half to the 365 over 140. So I get 49.24 milligrams. How long will it take for the sample to decay to 200 milligrams? Okay, so now we're going to set it equal to 200 and find the time. So how many days? So half, and then T over 140. Again, you could use this second equation too if you wanted. So divide by 300, 2/3 equals 1/2 to the T over 140. And then we need to get it out of exponential, so into logarithmic. So log of 1/2, because that's the base, of 2/3 equals T over 140 times 140, so that cancels. So time equals 140 log base a half of 2/3, which is about 81.9, and my label is in days. So 81.9 days. Let me go back here real quick. These two graphs will be identical. I was wrong on that. They will be identical because we've used the same numbers. We just rearranged it a little bit different on those. Okay, so Newton's law of cooling, the last example we're going to do here. A coffee cup has a temperature of 200 degrees. So Newton's cooling law, just to kind of bring that back, is T of T equals your surrounding temperature plus D naught E to the negative KT. And remember, D naught is your initial temperature minus your surrounding temperature. So 200 is my initial. So T sub 0 or T naught is placed in a room at 70 degrees. So that's your surrounding temperature. After 10 minutes, okay, notice everything's in minutes. The temperature of the coffee is 150. So this is actually T of T. And we don't have K. So it looks like we're going to be solving for K first. Okay, so I start with 150. Your surrounding temperature was 70 plus, for D naught, you need your start minus your surrounding. So 200 minus 70, which is 130, E to the minus K, and T was 10 minutes, so 10, because everything is in minutes. Make sure your labels all match up. So we're going to subtract 70. So 150 minus 70 is 80, equals 130, E to the minus K, 10. Divide by 130. So that's 8/13 equals E to the minus 10K. Change this out of exponential into logarithmic. So ln of 8/13 equals negative 10K, and divide by negative 10. And K is about, so ln of 8/13 divided by negative 10, and we get 0.0486. Okay, and that's different for every item that you have. So find a function. So our function here would be T of T equals 70 plus 130 E to the minus 0.0486 T. Okay, so we need T in there. So find the temperature after 15 minutes. So we need T of 15. So T of 15 is going to equal 70 plus 130 E to the minus 0.0486 times 15. We just put that into the calculator just like it is. E to the negative 0.0486 times 15. We get 132.71 degrees Fahrenheit. Okay, so we're looking for a temperature there. Part C, after how long will the coffee have cooled to 100 degrees? So we want to know if the final temperature is 100 degrees, how much time did that take? So we're going to plug in T of T to be 100, and we're solving for T there in the exponent. So we're going to subtract 70, so we get 30 equals 130 E to the minus 0.0486 T. Divide by 130, and you get 3/13 equals E to the minus 0.0486 T. Get it out of exponential, so you want log, or the ln of 3/13 equals negative 0.0486 T, and then you're going to divide by that negative 0.0486. So T equals ln of 3/13 over negative 0.0486, which is about 3/13 divided by negative 0.0486. About 30.2. Labels are in minutes, so minutes. All right, so there is your 4.6 kind of video over some of those exponential examples. So now you have a web assignment that you can start working through. If you have questions, feel free to reach out.